Hello, and thanks for joining us again on Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley. I am your host. Coming up today, we're going to be talking about a discovery on Mars. Yep, it's the remains of a glacier, and they think the ramifications of that could be really incredible for future human missions to the Red Planet. Of course, they could just pop over to New Zealand and get one, so I don't know what the big fuss is about. And a black hole has been discovered that's bigger than big. In fact, it's so big they've had to come up with another name for it, which I think will be very fitting. But this thing is enormous, and it's not an enormous black hole. It's bigger than that. Plus, we will be answering audience questions. Jeff wants to talk about time travel. Andy wants to talk about telescopes. And Neville wants to talk about the Big Bang and a different angle on the speed of light, which will be fascinating. That's all coming up on the next edition, this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us once again is his good self, the Reverend. No, he's a professor, though. Fred Watson, astronomer at large. Hello, Fred.
How are you doing, Andrew? I've never been revered, I have to say, so the Reverend is definitely the wrong title for me.
Well, you know, I thought I'd throw it out there.
Yeah, it's worth a try, yes.
Yeah. How you been since I saw you last?
Smashing, just wonderful.
Same day, different shirts.
Yes, well, I'd been out on the bike and I didn't want to go out on the bike in the shirt I had on this morning, so there you go.
Now, before we start, I want to send a little shout out to all the students of Dubbo North Public School, because I was there this afternoon for a program called Books in Homes. Books in Homes is trying to encourage children in primary school to read. And it's usually sponsored by a major corporation who have representatives there, and they like to send along a mentor to encourage the children to read. They couldn't find anyone, so they sent me. But it was really fantastic. We had the school assembly. The student council ran the assembly. The teachers just sat back and let them run the whole show. And they when they came to me, usually I do a little speech for these events, but no. They thought it'd be better if they interviewed me. So they read my bio and picked out 4 choice questions for me. That was really clever and really enjoyable to be a part of. So it was so terrific to be a part of it. And that's the first time they've done the Books in Schools, Books in Homes program. So it was really fantastic to be a part of. And if you are a school teacher, go to the Books in Homes website and see if it fits something you'd like to do in your school, because it's really worthwhile. And all the kids, every student in the school, 300 of them, got 3 books each to take home and to keep.
Fantastic.
They get them for free, and it's a fantastic program.
Yeah. Did they ask you any embarrassing questions, Andrew?
They asked me why this podcast is called Space Nuts.
Oh, because it's a good question.
And I said, I think it's because the people who listen are nuts about space. And they all laughed. So I thought, well, that's a good enough answer.
As good as any.
The truth is we don't know. Hugh thought of it, but he's never told us why.
No. Well, he thought he'd take 2 nutcases and put them in space. It's pretty straightforward.
That's probably the real answer. Yeah. All right, down to business. Now, we've got some interesting findings on Mars, and these are glacial remains. This is really exciting. And near the equator too, which might sound a bit strange to us Earthlings.
Yes, yes, that's right. It's known that there are deposits of ice on Mars. Most of them, however, have been identified near Mars's poles, as you'd expect, because that's where most of the ice is on Earth. But this is an occasion where a report of some topographical structures, by which I mean things you see on the surface, look as though you've got a kind of fossilized glacier there, or glacier, depending on where you learned the word. And they're being called relict glaciers. And that, so when you look that word up, you find that it often refers to
Fred Watson. No,
no, that's a relic. This is a relict.
I couldn't help it.
Yeah.
I couldn't.
No, you're
help
quite
it.
right. I'm certainly a relic from some past era, probably the 1960s. Anyway, a relict is something that doesn't belong there. It's something that's sort of out of its time, something that would have perhaps evolved, or a species, sometimes a species or a plant that is more suited to a time when the climate was different.
Like the Wallamai pine.
That sort of thing, yes, that's probably right. I don't know enough about the Wallamai pine to know that, but I know it belongs to a different era.
Yes, but they found them alive in the Blue Mountains, not far from where I am, just up the road, actually.
Yep, Wallamai, that's right.
Yeah.
So this is not about living organisms. This is about structures on the surface of Mars. And the thing that's got everybody excited is that this sort of speaks of glaciation and glacial remnants, but it's right on the equator. Nearly the equator. It's 7 degrees, 33 minutes south of the equator.
Yeah.
So it's at Mars's warmest area. That's the bottom line. But it could imply that there is actually ice not very far below the surface. Now, we know that in the Arctic, there is ice beneath a very thin layer of soil. The spacecraft, whose name is eluding me at the moment, but was in Mars's northern Arctic, landed on the surface, and was probably back in the early 2010s, I think, and scooped up sand from the surface, and sure enough, beneath it there was solid ice, a kind of permafrost of ice. And that is fine when you're at a latitude that might be 70 or 80 degrees from the equator, where you would expect it to be cold. But to find evidence that there might be something like that near the equator is exciting, because it might imply that there are large bodies of water that could be accessible to to human explorers on the planet near the equator. So it's at a place called Eastern Noctis Labyrinthus.
I love the names of places on Mars.
Yeah.
They're just awesome.
They're fantastic. That's right. And they all mean something, as do the geological eras on Mars. And I can't remember, there's the Noachian. The period we're in now is, if I remember rightly, the Amazonian period.
Yes, I've heard that.
And this structure that's being looked at belongs to the Amazonian period. So it may well be that there's, it's been dated to be very recent. And
just for the record, Earth is currently in the Anthropocene epoch.
That's right. Yes, we are.
Yeah.
A bit that we're tinkering with.
Just in case you didn't know.
Yes, exactly. It's been a conference where this was announced, but the work has been done by scientists at the University of the Mars Institute in
Maryland.
University of Maryland. That's the place.
Mm.
Maryland Department of Geology. That's what I was looking for.
Yeah.
We quite often get questions from Maryland, which is
we
nice.
do.
Yes,
and Arizona.
Yeah, and Arizona. That's right. Anyway, this is science that's been done basically from imagery of the surface of Mars, and you and I have spoken many times about the spacecraft that are in orbit around Mars, Mars Global Surveyor, Mars Reconnaissance Orbiter. These are the ones that have been able to take high-resolution images of Mars. And so what these scientists have done is they've looked closely at both the images and the radar results from Mars, which tell you how high and how deep things are. And what they're seeing is it's actually rock, but it looks like a glacier because it's got all the sort of features that we normally associate with glaciers, like moraines and these lateral deposits and terminal deposits. Yeah, crevices, thrust planes, all of that sort of thing. And they see all this stuff and say, this looks just like a glacier. But the temperature's too high for it to be a proper glacier. But what they are suggesting is that what you're seeing is basically deposits of volcanic salts, if I can put it that way, salty material that's been spread around by volcanoes. And I think this is I think if I remember right, this is a reasonably volcanic area. So, and it's actually, well, I'm going to read from our favourite crib sheet on phys.org. The presence of, no, wait a minute, let me read a quote from one of the scientists, actually a scientist at the SETI Institute and the Mars Institute, who's the lead author, Dr. Pascal Lee, who says, what we found is not ice, but a salt deposit with the detailed morphologic features of a glacier. In other words, it looks exactly like a glacier. And so what phys.org says is the presence of volcanic materials blanketing the region hints how the sulfate salts might have formed and preserved a glacier's imprint underneath. When freshly erupted pyroclastic materials, that's a mixture of volcanic ash, pumice, hot lava blocks, come in contact with water ice, sulfate salts, like the ones commonly making up Mars's light-toned deposits, may form and build up into a hardened, crusty salt layer. So the idea is that you've got a glacier, and then a volcano goes off, and you plunk this stuff on top of it, and it's almost like, you know, when you make a model of somebody's face in rubber or something like that, it's that kind of thing. That you're preserving the structure. And another of the authors from University of Maryland, Surab Subham, says this region of Mars has a history of volcanic activity, and where some of the volcanic materials came in contact with glacier ice, chemical reactions would have taken place. For some reason, the bit I was reading has just disappeared. I have no idea why.
It's called the internet, Fred.
Here we are. It's come back. This region of Mars has a history of volcanic activity. And where some of the volcanic materials came into contact with glacier ice, chemical reactions would have taken place at the boundary between the two to form a hardened layer of sulfate salts. This is the most likely explanation for the hydrated and hydroxylated sulfates we observe in this light-toned deposit. So it's a really nice piece of work. You've got something that mimics a glacier. What they don't know is whether underneath these salts, maybe not so deep, but protected to some extent from the heat of the sun on the equator of Mars, whether there is actually ice underneath. And of course, that's the big question. And I'm not really sure how you discover that without going there and digging holes in it.
Yeah, I guess that's the $64,000 question. And for future exploration and putting people on Mars, they probably need to know before they go, or do they send people there and go, well, we're going to land here and have a look around? But you'd really want to do your intelligence work before you left.
Yeah, that's right.
Because it's such a long journey.
Yes, exactly. But it's the sort of thing a robot might be very good at finding. The only problem is with some of these zones, Mars's geography is pretty rugged, and mission planners are always very reluctant to land a rover or a lander in a place where there's lots of boulders or lots of little craters or rocky outcrops, because it's hazardous for the landing process. You really want to land things in as safe conditions as you can, and of course that is even more relevant for human exploration.
Indeed, although Mark Watney would be able to help them out. He can get around on Mars.
That's right. That's correct.
Yeah.
Pretty good at that.
Yeah, I reckon so. But it's been quite a find, and it just keeps adding to the intelligence that's going to make Mars more and more exciting for a future visit. That's what really tickles my fancy, is that we know there's water there. I mean, there was one probe that dug a hole and boom, there was ice. And it's a stark photo, that one that they sent back. It was just a little scoop that did a scrape, and there was water ice just, millimeters below the surface. So it's everywhere, really. But this could be much better pay dirt, given that there's this potential significant amount of water, I suppose. Would that be fair?
Yes, and the critical thing is that you'd expect a permafrost of ice perhaps at high latitudes, but where this is, it's not at high latitudes. In fact, there's a very nice quote again from one of the authors of this paper. The desire to land humans at a location where they might be able to extract water ice from the ground has been pushing mission planners to consider higher latitude sites, but the latter environments are typically colder and more challenging for humans and robots. If there were equatorial locations where ice might be found at a shallow depth, then we'd have the best of both environments, warmer conditions for human exploration and still access to ice.
Yes. Yes, very exciting stuff. And if you want to read up on that story, by all means, jump on to the phys.org website. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and team with a go.
Space Nuts.
Moving right along, Fred, this story excites me too because it's one of our favourite subjects, that of a black hole. This one's a different black hole. This one is, like you talk about big black holes, the biggest ones as supermassive. They've decided this is too big to be supermassive. And that's what's really amazing about this story. This one's I just can't get my head around the gargantuanness of this. 33 billion times more massive than the sun.
Yeah, that's right. The colossal number. You're absolutely right. Its gargantuanness speaks for itself, doesn't it?
Yes, indeed.
Which is more than we can do. But yes, it's a supermassive. Sorry, it's a massive galaxy at the centre of a massive cluster, which is named Abel 1201. George Abel was the person who catalogued galaxy clusters some years ago. So its distance is about 2.7 billion light years. It's not on our doorstep by any means, but on the other hand, it's not at the other end of the universe. 2.7 billion light years is somewhere where you can actually make decent images of galaxies at that distance. And so the estimate of its mass has been gradually increasing. It's kind of the opposite story to Pluto, which was thought to be bigger than the Earth when it was discovered. And then throughout the 20th century, estimates of its mass just went steadily downwards.
Yeah, they ended up going, well, that's not a planet, that's a very naughty boy. That's what it was.
There was a lovely paper in the 1980s that predicted when Pluto's mass would be so small it would have disappeared. It's disappeared
from the list of planets.
Planets, indeed, that's exactly what's happened. Yeah. Anyway, this is the opposite thing. It's getting bigger, and so this, I think it was previously estimated. It's still big. It was previously estimated at something like 16 billion solar masses, but as you said, it's now gone up to nearly 33 billion solar masses. And the question is, I guess, that's on everybody's lips, how were these measurements made? Did somebody go there with a weighing scale, or what happened? And basically the answer is none of the above. It was done by gravitational lensing, that fantastic trick that astronomers have at their disposal to measure mass by looking at how objects a long way behind other things, the things whose mass you want to measure, looking how their light is distorted or bent by the gravitational pull of whatever it is that's at the middle of that object. And that's what happens. That's what has happened here.
So what have they decided to call it if it's too big to be supermassive?
Well, yeah, so we think that most galaxies, any ordinary galaxy, has what we call a supermassive black hole at its centre, including our own. Yeah. And the black hole at the centre of our galaxy, if I remember rightly, is 3.6 million times the mass of the Sun. But billion solar mass black holes are relatively common, and they are called supermassive black holes. But this wipes the floor with most of those. And it is an ultramassive black hole. Ultramassive, that's the correct term for it.
Now, if they'd really been thinking outside the square, they would have kept up with the modern vernacular and called it ubermassive.
Yes, that's right.
But I guess ultramassive will do the trick. That and then this is probably one of the biggest ever found. I'm assuming there's been bigger ones found, but not many.
Yes, that's right. And but this ranks among the top very few. I'm not sure where it stands in the records. The problem is, exactly as I guess this story highlights, the problem with things like this is how you measure their mass accurately. And so one way of doing it is if you've got a black hole that's actively gobbling up stuff around it, that can give you an estimate of its mass, because what happens is the stuff that's being sucked in gets swirled into what's called the accretion disk, this disk of material that's on its way down to the center of to the black hole itself. And you can actually measure the velocity of material swirling around in that accretion disk. And that gives you a measurement of the black hole's mass. But this galaxy, it's supermassive, it's hypermassive black hole, I beg your pardon, it's ultramassive black hole, get the word right, Fred, is quiescent. It means it's not actually gobbling up stuff in the way that would be helpful if you wanted to measure its mass. And that makes it hard to see. Exactly, yes. So you can only detect it by its gravitational influence on its surroundings or on the light passing it from a background galaxy. And it turns out that by chance there is a galaxy almost directly aligned behind this particular one at the center of the Abel 1201 cluster. Mm-hmm. And so it's by looking very carefully at very detailed high resolution images of this particular galaxy that a faint image of the distorted galaxy behind, or a faint distorted image of the galaxy behind it has been measured and analyzed. And it's that tells you that at the center of the foreground galaxy, the one that's doing the lensing, there must be this ultra-massive black hole. And I might just add that some of these observations were made with an instrument called MUSE, the Multi-Unit Spectroscopic Explorer, which is commonly used actually by Australian astronomers. It's one of the instruments of the Very Large Telescope, the European Southern Observatory's flagship instrument down at Cerro Paranal in Chile, or up at Cerro Paranal from here. So that's basically the way this work has gone. It's the analysis of the gravitational lensing effect of the galaxy that has led the scientists who are based, at least one of them is based at the University of Durham in the United Kingdom. I used to have a lot to do with that university when I was building instruments a bit like MUSE, the one we were just talking about. So that's where the results have come from, this measurement of the gravitational distortion.
Okay, I'm just looking through the list of black holes, and Abel 1201 sits at 1, 2, 3, 4, about 7th on the list.
That's right.
Now, that's based on certain limitations, but I think the biggest one is TON 618,
okay,
which is a hyperluminous broad absorption line radio loud quasar and Lyman alpha blob.
Yeah.
Get all that science, and they call it a blob.
A blob, yeah. So what that's telling you is it's the way that the accretion disk is behaving, the way it's gobbling up material that's been used to measure its mass.
Yeah.
So that's has its mass measured in different, in a different framework. I notice in the article that I'm reading that we have two different numbers for this one. I said it was 1201, but it's somebody's got the numbers the wrong way around, and it's 1021, I think.
Yeah, well let me see. Well, I've got 1201 on this list.
All right, so maybe it's 1201. Maybe the 1021 is the incorrect version.
That's a typo.
It's a typo, that's right. But when it's a typo like that, you don't know which one's the right one.
Yeah, well, they've done them both a few times in the article, so it's yeah,
that's right.
Pretty sure it's a typo. I do that all the time.
Yes, so do I sometimes.
I transpose letters and numbers all the time. It's terrible. You should see my bank account. I think I'm rich, but apparently not.
Yes, all right. You just get the millions in the wrong order.
That's exactly right.
So the upper limit for these things is thought to be about 50 billion times the mass of the sun. And this is pushing it a bit. And that's why it's of interest. You know, it's not clawing at the number 50, but 32.7 is a bit near that. And one statistic that I really like is the diameter of its event horizon. You know, the event horizon of a black hole is the point beyond which there's no return. It's the point where you can't even see light coming from the black hole. Yeah. And it is more than, as they quote here, more than 1,290 astronomical units. An astronomical unit is 150 million kilometers. It's the distance between the sun and the Earth. Neptune is about 30 astronomical units from our sun. But this thing is, well, so that would be a diameter of 60 astronomical units. This thing is 1,290 astronomical units. It is huge, absolutely enormous. Remember that if the Earth, if you had a black hole with the mass of the Earth, its event horizon, if I remember rightly, it will be 18 millimeters. This is 1,290 astronomical units. So it is a very big black hole.
It's gobsmackingly large. It should be called the gobsmackingly massive black hole.
Yes, that's right. That was an expression that I think grew up in Britain, so it's very appropriate that the gobsmackers of the United Kingdom should put their name to it. But instead, we've got an ultramassive black hole.
Ultramassive's good. I like the word. It works, and there aren't that many of them, as I said. And it's and I suppose it wasn't that long ago when we sort of started the podcast and started talking about black holes that we said, look, they only come in two sizes. We've never found a middle-sized one. Well, now we have. And now we're finding all sorts of sizes. Yeah, just a vast spectrum of them. They just keep popping up. Darn it. Although they can tell us so much, they also don't tell us a lot. They only tell us what suits them. They're so mysterious.
It's true. That's because nothing comes out of them. It all goes in.
That's right. Gosh, imagine what we could learn if we could just get our heads in there and have a bit of a squiz.
Yes. Just in the gazillionth of a second before your head turned into a spaghetti.
You could just say, oh, I got it. Too late.
Too late, yeah.
I know everything. Yes. Too late. Damn. And you couldn't even put a probe in there to send a signal because a signal wouldn't get out.
No, it wouldn't.
You couldn't do anything. It's just impossible.
What you've got to do, Andrew, what you've got to do is find a white hole that's churning everything out, and that might tell us the secret of the universe. But we haven't found any yet.
What we need is to observe a collision between a white hole and a black hole.
Ooh, now that would be sensational, yeah.
I reckon that would solve the problem.
That would rattle LIGO a bit, wouldn't it?
It would do. By the way, if you want to follow up on that story, you can go to the sciencealert.com website, or you can read the research in the monthly notices of the Royal Astronomical Society.
Okay, we checked all four systems and keying was a go.
Space Nuts.
That's us, Fred. Now we've come to the next part, which was after the previous part, which came after the part before that. But this is the part where we hand it over to the audience, and we get all sorts of questions that we like to sit and laugh at because we don't know any of the answers, and we just make it up as we go along.
Don't tell them that. Oh, of course they already know, don't they?
I think they do. Yes. But we often get time travel questions, and Jeff is definitely of that ilk.
Hi, Fred and Andrew. This is Jeff in Dublin, Ohio.
I'm not a big NFL fan, so let's not talk about the Bengals. Anyway, I have the Godowka experiment about time travel. If I'm standing on the Earth today and I want to go back 10 years with my brand new time machine, wouldn't that mean that I would end up in the middle of space since the Earth has moved several million miles 10 years ago? I'd really like to know because it could be the basis for a cool science fiction story. First-time listener, first-time caller. Really glad you guys do this show. I love it. Take care.
You too, Jeff. Thank you so much. He's absolutely spot on. I think we've been over this once before. Just trying to remember if I've read it somewhere in a science fiction novel. But yes, if you were going to travel back in time, you would have to come up with some pretty savvy calculations that were exactly right.
If you wanted to survive, that's right.
Yes, and end up in the right place.
Yeah. So the typical place in the universe is there's not much going on. It's pretty dire. It's empty space. But if you and Jeff's right, the rotation of the galaxy would have carried the whole solar system along by 10 years worth of 200 kilometers per second times however many seconds there are in 10 years.
Oh, no.
Yeah, it's a long way. So that's right. And, as far as we know, backward time travel is impossible because it conflicts with all kinds of causal things. It's philosophically not possible to have backward time travel, even if we had a mechanism for it, which we haven't. The forward time travel is different. You can go forward in time by doing the trick of going very fast for a long distance and then coming back again, and you're much younger than the people you've left behind.
Yeah. Well,
So
they've proven that with atomic clocks, haven't they?
Yeah. Oh, yes, that's right. Yeah.
You can go forward,
but not backwards. So, and it's probably just as well, because who wants to be in a typical place in the universe where it's completely dark, nothing's happening, it's a complete vacuum, and there's nothing on TV.
But assuming you could, which we like to do on this podcast, assuming you could go back in time, you would have to calculate precisely where you needed to be at the exact moment of transfer, so that you'd turn up on the Earth and not under it or too far above it and come crashing back down, or be just slightly out of reach and watch it, drift away.
Yes.
There would be very little room for error. In fact, there'd probably be none, I would imagine, with that kind of thing.
Yeah, so an interesting question.
And you'd have to allow, I know this is going to sound silly, but you'd have to allow for continental drift, wouldn't you?
Maybe. Yes, you would. Well, wait a minute. Continental drift is typically 3 or 4 centimetres a year. So
yeah, well, you wouldn't, but if you didn't allow for it, that's 30 centimetres off target.
Oh, you would be, yeah. But that might be acceptable. Unless it was 30 centimetres under the surface of the Earth, in which case you'd feel embarrassed. But I was going to say, you'd probably have to allow, you might have to assume, so you go back in time, you're going back in one coordinate, one of the space-time coordinates. And that would mean that wherever you landed, you would probably have the same velocity through space as you had when you left, which is a combination of the Earth's rotation, the Earth's revolution around the sun's revolution around the galaxy, and our galaxy's motion in the local group of galaxies. That dictates what your motion is at any given time. And it would, presumably, I have to defer to you as a science fiction author, you would come back to wherever it was in the past that you were going to with those same velocity coordinates.
Sounds feasible to me.
Yeah.
It sounds like a reasonable assessment.
So that might mean that, if you got it really wrong, you might bang into something else that you didn't want to bang into.
Yeah, yeah.
Which is
Wouldn't it be awful if you just did all this, worked it out, got exactly the right parameters and calculations and target points, and then forgot about the moon?
Quite so, yeah.
Yeah. Theoretically possible, Jeff, because we are capable of backtracking our calculations to work out where we would have been. So theoretically possible, but impossible in all practical terms. Yeah.
That's right.
Yes, unless you can gather in all the power of the universe at once.
Quite.
Let me know how you go with that, Jeff. Thanks for your question. Lovely to hear from you. And go the Bengals. Now to Andy, who is in Wisconsin. You nuts talk a lot about radio telescopes and optical telescopes to detect things in space, whether close to Earth or very far away. Science fiction talks about a lot of passive sensors versus active sensors. If telescopes are considered passive sensors, how far into the future is the technology for active sensors to detect things like objects in the Oort cloud or to look into gas giants? Also, not that I'm tired of listening to you guys, but have you considered having a guest on the show? We have had guests on the show, but not very often. But yes, we have done it before. We'll probably do it again. And he goes on to say that I'm sure Professor Fred knows a lot of great candidates. Keep up the great work. Thanks, Andy. Yes, we'll take your advice seriously, and we'll certainly look to that in the future. We just don't want it to become too much of a talk fest with too many people. I mean, most people say we just like it the way it is. Don't fix it if it's not broken. But occasionally we'll have somebody on, yes, if we've got a good reason to. Andy wants to know about telescopes. What does the future hold for active sensors, basically?
So we do use active sensors, actually, in specialized cases. And you would know what they are because we've seen images that they've created. So some of the world's great radio telescopes, and the dish that was the sort of past master at this, and unfortunately is now past, was the Arecibo dish in Puerto Rico. Yeah. What you can do is bounce radar signals off asteroids, passing asteroids, and that gives you a much higher resolution image of the asteroid than if you were just looking at it with an optical telescope, which would be a passive sensor. But the limitations of that technique really hold you to be inside the solar system, because you're talking about travel times measured in minutes or hours for the radar signals to go through the solar system. If you were interested in anything beyond the solar system, you're talking about travel times that are just too long. Probably the only object that you might want to bounce it off would be Voyager 1, which I think is 20 light hours away, I think 20 or 22 light hours from so that you'd have a 40-hour light hour return of the active signal, and you might be able to create an image of Voyager 1 doing that, which would be fantastic, except we know what it looks like because we built it. So, so a little bit dreary. So active imagery happens, but you're limited by the laws of physics. You're never going to be able to image the planet around of another star without waiting. For example, even that little planet around Proxima Centauri, you're going to have to wait getting on for 9 years to get the return signal, whose intensity would be so low as to be undetectable, I suspect, even by the square kilometre array.
Oh, okay. So it's not an easy thing to do at length, basically.
That's right. You can do it in the solar system. It's done almost exclusively by radio telescopes. The optical telescopes tend to be completely passive.
So when USS Enterprise uses its active sensors over, several light years, it's really just breaking the laws of physics. Which
I believe that series does rather a lot.
Yeah, well, why not? It's science fiction. You can do whatever you damn well please, really. That's what I love about it. You can just break all the rules. I certainly have. There you go, Andy. Can be done, but not very far, because it just isn't physically possible. Do you like that? Physically possible?
Oh, yes, physically.
Yes. Thank you, Andy. Great to hear from you. And finally, we'll go. This is actually in the neighbourhood. We're going to hear from Neville, who is from a town called Kirban, more of a village, I would suggest, but it's basically between here and your old stomping ground of Coonabarabran. In fact, it's nestled in the valley between Gilgandra and Armatry is Kirban. So thanks for getting in touch, Neville. He says, "G'day, Andrew and Fred. I live between Dubbo and Siding Spring and can see Fred's telescope from my farm. I've listened to you and Fred sparring on space matters for many years, courtesy of ABC Radio. On Discovering Space Nuts, I binged for about 100 episodes until I caught up and looked forward to the next episodes. 2 questions. The singularity to start the universe, A, was a single hydrogen atom, or B, as I suspect, a singularity, the mass of the universe? Which is it?" I mean, the next question is completely different, so let's just do them separately.
Talk to that one. Yeah, so it's a singularity which I guess has to somehow embody the whole energy mass content of the universe. Unless the process in which it was created did that. And this is where, physics breaks down. We really have no idea. We can talk about what happened within the first, I think, 10 to the minus 33 of a second or thereabouts after the Big Bang, which was when the inflationary period started. But what the singularity was like, what created it, the standard mantra is in the beginning there was nothing and then it exploded, and that's about all we can say. So maybe it was a singularity with the mass energy content of the entire universe embodied in its 0 dimensions.
Wow. That's something to think about, isn't it?
It is.
Yeah. All right. Second question, and this one I like because we talk about time travel and going faster than light, which we've done on this episode and the last several episodes. Recently, you talked about traveling faster than the speed of light. When you go through the sound barrier, a sonic boom is created. What would happen if you passed the speed of light barrier? Would all the photons generated from your spacecraft crowd up in front of you and blow you to bits?
Yeah, probably. That's as good an estimate as possible. But actually, Neville, we know what happens because we can make things travel faster than the speed of light in a medium. So the thing about the speed of light being the ultimate speed limit of the universe is that it's the speed of light in a vacuum. If you have photons, particles of light, entering a medium faster, so the local speed of light in the medium has to be lower than the speed of light in a vacuum. That's how refraction works. So, if you enter glass or even air or water, you've got a photon coming in from space, hits this thing where the speed of light is lower, but the photon is traveling faster than that. So what does it do? It does exactly what you get in the sound barrier. You get going through the sound barrier creates a shock wave, which you can hear as a bang if you're on the ground. And going through the light barrier creates a shock wave in the form of photons of light, which is called Cherenkov radiation. And that's extremely useful because photons coming in faster than the speed of light, high energy photons, gamma rays, for example, hit the atmosphere and they generate flashes of blue light, which is the Cherenkov radiation, which can be detected by telescopes. And that's why these high energy telescopes are called Cherenkov telescopes. And in fact, there's a big one being built or being considered at the moment, an array of large telescopes of that kind called the CTA, the Cherenkov Telescope Array, which will go not very far from the ELT, the extremely large telescope at Cerro Amazones, and again not far from Cerro Paranal, where the VLT, the very large telescope, is in northern Chile. So that exact process, particles of light traveling faster than the speed of light, happens and is useful to us as astronomers.
Fantastic. Wow. Okay. So he's kind of onto something.
Yeah. Thanks for mentioning it, Neville.
Yeah. And say hi to everyone in Kirban for us. He just did it.
Both of them.
both of them. And that includes the dog. No, Neville, lovely to hear from you. And thanks for catching up. It's nice to hear from somebody who used to listen to us on the radio all those years ago.
All those years ago.
Yeah.
So we're just youngsters.
Now, one more thing. Remember we were trying to figure out why Hugh called the podcast Space Nuts? It wasn't him. It was a fellow named Foxy. I don't think we've mentioned Foxy before, but he recorded all the intros and the IDs for Space Nuts. And when Hugh told him we were getting ready to launch a space science podcast between the two of us, he never explained why he used the name at the time. So we're all still in the dark about it.
Okay.
Yeah. But he's a super uber space fan himself. So I guess he was the one that was nuts about space, and
I think it's more, he just took one look at us and said, God, those guys are nuts.
Yeah, probably.
Space nuts.
That would be it. Hello, Foxy, by the way.
Yeah.
Yes. So not Hugh's fault, which gives me one less thing to stir him up about. Damn. Don't forget, if you've got questions for us, jump on our website, because that's where you send them via the AMA tab or the send us your voice question or voice message tab on the right-hand side. If your device has got a microphone, it's as simple as that. Or the text version, yes, we take those too. We've done a few of those lately. And don't forget to tell us who you are and where you're from. And don't forget about the Space Nuts Facebook page, but also the Space Nuts podcast group on Facebook, which is very active, where you can talk to each other about astronomy and space science and tell awful jokes. Not that I would ever be found guilty of doing that. No. Check out our latest hit TikTok. Yuck. All right. That brings us to the end. Fred, thank you so much.
Always a pleasure, Andrew, and we will speak again soon, I hope.
We will indeed. Fred Watson, astronomer at large, and thanks to Hugh in the studio for deflecting blame. And from me, Andrew Dunkley, goodbye. We'll see you on the very next episode of Space Nuts. See ya.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.